Hi everyone. So you were assigned a table that looks a lot like this to do for homework tonight because the quizzes on this type of stuff were a little sad. So we're going to, hopefully by now you've at least tried to do it. Although I'm sure most of you have not. But either way, I guess I can't control that from here. So let's get cracking. So the first one asks us, a ball is the situation. A ball is dropped and is falling down. We've seen this a million times in class before. If you recall, it is simply a motion diagram that has something that looks a bit like this. And this one gets a bit further away, a bit further away, a bit further away, resulting in a downward accelerating motion, and of course the delta V arrow is going to be in the direction of the bigger arrows, which is this way. That's a trick you can use. Delta V arrow always points in the direction of the bigger arrows. Force diagram, if you think about the objects that are interacting with the ball while it is falling, and here's where a lot of people got stuff wrong. Your hand is no longer interacting with the falling ball. All that is interacting with the ball is the earth. So you can list earth and then simply draw your force diagram. You can have here's positive y, positive x, and so this would be force earth on the ball. And so now the question is, how do you know if the motion diagram and force diagram are consistent? In class, we learned that the delta V arrow occurs in the direction of the unbalanced force, or now we know that acceleration occurs in the direction of the unbalanced force. So that is how we know. So when it asks, how do you know they are consistent, you say the delta V arrow is in the direction of the unbalanced force. Alright, so moving on. A ball is thrown upwards after it leaves your hand. So it's thrown upwards, the situation after it leaves your hand and before it reaches the top of the flight. So meaning it is not in touch with your hand anymore. It is in the middle of the air. So your force diagram, similarly, will look something like this. Oh, sorry, that's wrong. That's what that is. Try that again. So it's going up and slowly coming to a stop. So it's still going in the positive direction. This may look familiar to some of you from your quiz, but the delta V arrow, as per the one previously, is also still in this direction. I was using the thick arrow to show delta V. Alright, and so there you go. And again, since nothing else is interacting with it except the earth, I should probably have a negative and positive here, negative and positive here, plus y, plus x, and that. Alright, and so force diagram, lo and behold, is the same because earth is always pulling downward. Alright, and same thing for here. Okay, the delta V arrow is in the same direction as the unbalanced force, and it's coming to a stop, so we know the delta V arrow is this way. A ball is thrown down, so the difference here is that rather than starting from just stop, the ball will be starting from a faster initial velocity. So we can do something like that. Doesn't really fit in the box, but you get the idea. Make this negative, positive, make this negative, and then delta V once again is in the negative direction. Alright, and so now it depends on when in this diagram we decide to start looking at the ball. I'm going to assume that the ball is not in your hand anymore. Well, even if it were, if the ball were in your hand still and you were physically throwing it down, this would still be the motion diagram because you would still be throwing it down, you would still be accelerating downward. The only difference is that there would no longer only be one arrow because you have your hand interacting with the ball and you have the earth. And so there would be two arrows down. It would be force earth on ball, and this arrow should be the same size as the rest of these. Maybe I should fix that. So you would have this arrow downward, and then this extra force here is the force that you are exerting downward with your hand while you are pushing it. Alright, and that gives you this. And same thing, the earth and the hand are both in the same direction, so the sum of the forces is in the negative y direction. This is positive y. And so once again, same thing, the delta V arrow is in the direction of the unbalanced force in the negative direction for all of these. Okay, let's move on then. So, let's see. Go. So, a football is landing on a cushion, and the cushion is being compressed. So, our object of interest is still the football. It's still the ball. And so, if you were to draw a picture of this, it might look something like this. If this were the cushion, and then this were the very egg-shaped football. Laces. There you go. You can get the idea. So when the ball is landing in the cushion, it is starting from some sort of initial velocity, and as the cushion compresses it, it slows down and eventually comes to a stop. So in this case, if this is positive, this is negative, the delta V arrow is, you guessed it, in the positive direction, because the arrows on top are bigger and the bottom is smaller, so the delta V arrow is going to be pointing up. It signifies something moving in the negative direction but slowing down. And so once again, the force diagram, now it's a little bit different. We have two objects interacting with our football. We have the cushion pushing up on it, right? And we have the earth pulling it down. Now, since the delta V arrow is pointed up, because it does come to a stop eventually, we know that the unbalanced force should be in the upward direction. So this force here is going to be bigger than this one. So this is force cushion on ball, this is force earth on ball, and this one is in fact bigger than this one. And so how do we know it's consistent? We know because the unbalanced force is up and the ball is moving, and I'm going to go off here because it's hard to write small on this thing, in the negative direction and coming to a stop. So once again, delta V is related to the unbalanced force, what we call the total sum of forces. If you don't know what this symbol means, you didn't watch my other video. Go watch my other video. Rabbit sits in its cage. Well, for rabbit sitting in its cage, presumably it's not moving, so you would just have v equals 0, not moving anywhere. You can put your plus and minus wherever you want, doesn't matter, it's not moving anywhere. So for this force diagram, we've got two objects interacting. We've got the earth, we've got the cage, Not to be confused with Johnny Cage from The Test. Not Johnny Cage, Nicolas Cage. Johnny Cage is a Mortal Kombat character. My bad. So in the cage, and we've got the two forces. They are balanced. Notice they're the same size. It's going to be force cage on Bunny. This is going to be force Earth on Bunny. Sorry, those should be a little bit smaller, but you get the idea. And are they consistent? Yes. The Bunny is stationary. Still. So delta V equals 0. And there's no unbalanced force. Okay, moving on. A matchbox slides down a smooth book cover. So this is going to be a little different. If we have our book cover, so here's our book. Notice how drawing on a computer does not help my drawing abilities at all. So here's our book, here's our matchbox, and the matchbox is sliding down the book cover. So our motion diagram, in this case, if we call this, well, let's call this positive, let's call this negative, you're going to have this not moving with a constant velocity, but slowly getting faster in this direction, because the acceleration from the Earth is still going to affect it. And so in this case we'll have a delta V arrow going this way. V. And so now here's the tricky bit. Because this is at an angle, what I'm going to do is I'm just going to pretend like well, I'm not going to. I'll keep the axis normal. So here's our axis. And what are our forces? We've got the force exerted by the book on the matchbox. We have the force exerted by the Earth on the matchbox. And that's pretty much it. And so if we draw our matchbox and draw our force diagram, we've got one here. We've got, sorry, not here, because the matchbox isn't pushing up on it, is it? It's pushing off to the side. So really it should look something like this. We've got the Earth pointing down, and we've got this going this way. And so if you'll notice, here you have a force that is going off at an angle from everything else. So what I would do is I would break this up into its components. If you don't know what I'm talking about, I don't feel bad because you didn't watch my video. So we'll break it up into its component vectors. One will go this way, one will go this way, and you'll notice that this vector, because it's not moving in this direction, will balance out this one. So using geometry symbols, right, these two are the same length. And then this vector, this component of this downward vector, the Earth, and oh, I'm sorry. You know what? I made a mistake here. There's no force on this from this. I don't know what this force is. It was a magic force that I put in there by mistake. So the reason it falls down the page at all is because there's this component of the Earth, the force that the Earth is pushing on it with, pulling it down. Let me redraw this. Oh shit. Undo. Very slow to respond. There we go. So yeah, the reason this falls down the book at all is because there's this component of the force that the Earth is pulling on it with. So this is going to be the force Earth on Matchbox, and this is force book on Matchbox. And so this component of the Earth pulling down on it is what causes it to go down the book. And so over here we can write yes, unbalanced force pointing down the book. And delta V So down the book. Okay, so again, delta V and force, unbalanced force, are pointing down the same direction. Lastly, we have a hockey puck slides across an air table. So the point of having a hockey puck is to say that it's moving with a constant velocity. There's no forces being exerted on it. So presumably it's frictionless. There's nothing to stop it. So delta V equals 0. And so again, our force diagram. That's an X. We'll have just two objects: force table, well, technically force air, right? Because there's air holding it up on puck, and this will be balanced. These two are the same, and this is force earth on puck. Sorry about the handwriting. And so, do they correspond? Yes, because there's no unbalanced force. Unbalanced force. And delta V equals 0. Okay? And there you have it. And so that's how you solve this. Notice that every time I ask if it corresponds, I'm asking basically, are the delta V arrow and the unbalanced force in the same direction? If they are, then they do correspond. If they don't, then you probably did something wrong, unless it's a problem that I'm asking you. So good luck. Review this. Go watch my other video, please. I know it's long, but you'll get over it. And I'll see you tomorrow.